Hello everyone and welcome back to the channel. So as I mentioned in my last video, I'm going to try and hone in on a few specific features that are fairly popular of some popular technologies that I can then eventually use in some systems design videos. Today we'll be talking about Kafka transactions, which are a very important feature for ensuring exactly once processing. Now, despite, I'm sure, a lot of software engineers being used to transactions from transactional relationships, due to our large supplies of money and limited social skills, that is not ultimately what I will be talking about today. We'll be talking about Kafka. So let's go ahead and get into it. All right, so we read the Kafka paper on this channel, which I believe came out in something like 2011. But today we're going to be talking about transactions, which are a feature that got introduced in version 0.11, which was 2017. Now, I've recently been getting cooked at work because I don't know anything about these, so it's time for me to go ahead and learn about them. Basically, transactions are going to allow us to achieve exactly once messaging in Kafka, which up until this point, people kind of assumed wasn't exactly easy to implement, or if you could, that it would be really, really slow. Here's how Kafka does it, and it's actually not that slow, so we'll go ahead and talk about it. So basically, in addition to supporting exactly once messaging, Kafka also supports at least once and at most once. We'll talk about those in a second and what that means for producers and consumers of Kafka messages when they are configured that way. So just to quickly recap what Kafka is, how it works in general, basically we've got all of these topics, and topics can be broken down into partitions. Within a topic partition, it's effectively just a log, and so messages are ordered within that log. Every single consumer of a topic partition is reading every single message, and they're receiving them all in order. Now, there are going to be leaders of a topic partition, and there are also going to be followers or replicas. For the sake of today's video, we're not really going to be talking about replication in Kafka very much. I may actually go ahead and talk about that next week because I think it's relevant as well. But basically, if we have a producer, the producer is pushing messages over here to the broker. The broker is then responding with acknowledgments back to the producer. The producer may behave differently on whether or not it receives that acknowledgement, depending on how it's configured. And then all of the messages are supplied with an offset in the broker. So, all of these have some amount of data in them. And then in turn, the consumer is now reading every single message in order from the broker. And in addition to that, it has an offset associated with the last message that it's read. So it may store the offset locally because that way it'll say, first I'm going to get these two messages. Now I've consumed up until and including offset 7. Oh, and now the next time I pull from the Kafka broker, I'm going to get these guys because I haven't seen them yet. That being said, we also may want some fault tolerance. So sometimes the consumer may actually commit offsets to something like a separate Kafka topic over here, basically saying, oh, I've seen offset 7. And now, oh wait, I've seen offset number 10. So that way if it went down and came back up, we could start consuming messages from the last known offset. Now this is going to leave us with a few different types of failure scenarios, and we're going to discuss them now. This is where things like the at most once and at least once modes came into play before Kafka transactions. So basically for both producers and consumers, you can configure them as either at least once or at most once in terms of how they process messages. So if I'm a producer and I'm configured to produce messages at least once, basically what this means is I try and send messages to a broker. The acknowledgement comes over here. If I don't get that back, I then try again. Simple, but it just means that every single message is going to, reattempt produce until we get an acknowledgement. On the other hand, if we want to make sure that messages are only going to be produced at most once, if we don't receive an acknowledgement back from the broker, doesn't matter, we still don't retry because maybe that acknowledgement just got lost somewhere, there was some sort of network failure. It doesn't necessarily mean that the broker didn't process the message. On the consumer side, at least once basically means that we're not going to commit our message offsets until the message is fully processed. So in practice, this means that if our consumer goes down, before it actually commits those offsets, it may come back up, look at its old offsets, and then reread messages that it already read but hadn't committed offsets for. Then there's at most once with consumer, which is basically just saying every single time I read messages from Kafka and I pull new messages, I also consume the offset or the highest offset of those messages that I pulled, meaning that even if I went down and come back up, I'm never going to read those messages again. That being said, the consumer could have gone down before it actually processed those messages, hence the at most once piece of this. However, at least and at most once functionality is nice when you care about approximate results. If you need exact results, then maybe you want exactly once message processing. So let's go ahead and introduce what exactly once message processing is trying to do, at least within Kafka. So basically the idea is this is going to be a kind of input, process, output cycle. So we've got some sort of producer. It's producing data to an input topic over here. And basically we now have a consumer that's reading data from the input topic, producing data to an output topic because it's doing some processing on each input message, and at the same time also committing offsets to the input topic so that it's handling every single input message exactly once and producing exactly one message to the output topic in response to the input topic message. Now, like I mentioned, internally, committing offsets for a given input topic is identical to writing to an additional output Kafka topic because the offsets are themselves just some internal topic called _consumer offsets. So basically what this means is that if we can solve the problem of having atomic Kafka writes in general, we can solve the problem of exactly once processing because it means that we can both produce an output message or multiple and also commit the offsets to the input topic atomically, meaning that both of those writes go through or neither of them do. And only once those writes are considered committed can downstream consumers actually see those as valid. So basically either 2A and 2B need to both commit or neither can, and no one can read them until they both commit. That's a big part of this. Okay, so the question is, we understand that's kind of what transactions are doing, right? But transactions are acting very much internally to the Kafka ecosystem. Like the internal topic, or the input topic and the output topic are very much both within Kafka. What this isn't valid for is publishing to something like an external store, right? So if this consumer were also publishing to some sort of database, that database isn't in Kafka. So it's possible that it would publish here, but never committed the offset for this message, and then we're unable to roll this back. And so that is not going to be a valid use case of transactions. Same idea if for whatever reason the processing of every single input logic that's being done is using some sort of non-deterministic logic or going to some sort of external store to process that message. You may be able to process the message again and still have exactly once processing, but you may not get the same result the second time that you process a message. And then finally, one other thing to note about transactions, this is the term that they use in the article, is that they are not atomic reads. If I publish multiple different messages atomically as part of a transaction, it's not exactly easy for a consumer to say, oh wait, I know that all three of these messages are linked as part of the same transaction because they're on different topics, and a consumer is not necessarily reading all of those at the same time, so it's not trivial to basically make that distinction. Okay. So now we're going to talk about some failure scenarios, right? Because even though we kind of implicitly mentioned these already, let's just make them a little bit more explicit and then talk about how transactions are going to solve all of them. Number one is just that a producer can publish the same message multiple times to a broker. Maybe the broker tries to acknowledge a message, but it just fails, and now a producer publishes it twice by accident. So that's what happens when the acknowledge RPC fails back to the producer. Number two is that, like I mentioned, it's possible that a consumer can fail after processing a message, but before actually committing its offsets back to the broker. So now we have an output message, but we haven't committed our offsets. And so when the consumer comes back up, it's going to publish another output message for the same input message, and now we've published two output messages. And then finally, another thing that can happen is this concept of zombies. We've seen these in the past when we've spoken about things like fencing tokens. Same exact idea in Kafka, but basically, let's say the consumer, for whatever reason, only fails temporarily, right? Maybe it has a network partition, maybe it's got a super long garbage collection, something like that. We assume the consumer is down. We go ahead and bring up another to do the exact same thing as it, and then the consumer that we previously thought was dead comes back up, and now all of a sudden the consumer and the new version of the consumer are both consuming from the input topic, publishing to the output topic, and we have duplicate messages there. So what we have to do is figure out a way to kind of fence off this zombie, and we'll talk about that in a second. So the first thing that we do is going to solve problem one of basically a producer that publishes messages twice. They solve that in Kafka with this concept of idempotent publishing. So basically, if I am a producer that is hoping to produce transactional messages or exactly once messages, the idea here is just that every single time I make an API call with a batch of messages to a Kafka broker, I'm going to assign that some sort of sequence number. And so for whatever reason, the broker applies messages, but that doesn't actually go through getting back to the producer, and the producer retries with that same batch sequence number, the broker is going to now reject those messages. So basically they call that idempotent publishing. Clearly that's going to stop us from publishing the same messages twice. So that's fairly trivial. Another thing that we're going to do is preventing zombies, right? So this is case number 3 over here, where the consumer goes down and we bring up another consumer. Basically, every single one of these consumers is going to be configured with some sort of transaction ID. And so basically, when a consumer gets configured with a transaction ID, it gets registered with Kafka on startup. And in the process of registering that transaction ID, what we're also going to do is basically give every single invocation of the transaction ID an epoch number. So for example, if I'm a consumer and I originally get registered with transaction ID X, I'm going to go to this component called the transaction coordinator, and the coordinator is going to say, oh, I've never seen this ID before, so you're epoch 1. Now let's say this guy goes down, and then this guy comes up instead second. He's also going to go to the transaction coordinator. The coordinator is going to say, okay, this is epoch 2. It's then going to go to basically all of the Kafka topic partitions that are relevant for this transaction and say, listen, if you're part of, if you're part of this transaction, if you're one of the partitions that's going to be receiving messages from this transaction, you should reject any messages from producer with ID X but epoch 1. And so basically this Kafka output topic now has a slight bit of additional validation to say, hey, listen, I'm not going to accept messages from you because you're an old producer and this is likely a zombie. One caveat of that is that when you choose a transaction ID, you want to be sure that every single component that's using the same transaction ID is reading from the same input topics and writing to the same output topics. The reason for that is that we're only performing this validation right here of saying no on the topics that are registered with the current epoch. So basically this guy over here is coming to the coordinator and saying, I only care about this particular topic partition. So to kind of try and make that more concrete, let's say this guy is the epoch 1 producer over here, and originally in epoch 1 we're writing to topic 1. Now this guy maybe goes down for a second, or we think it goes down, so we bring up another producer, again with transaction ID X. This guy gets assigned with epoch 2, but for whatever reason in this invocation of the producer we're only writing to topic 2 and topic 3. So these guys are now going to prevent any messages coming in from a producer with ID X and epoch 1, but this guy is not over here. And so if we try and write to it from a zombie, it's still going to allow that message. Now, is this inherently problematic? In some ways, maybe, because this guy also may be trying to write messages over here as well. And so these are going to go through and go into the broker, but these are not. So ideally, your transaction ID should be used on processes that are all reading from and writing to the same output topics. Okay. Now, the first thing that we're going to talk about is actually how, if I'm a producer, or rather if I'm a consumer and I'm getting data from an input topic and I want to make an atomic write to multiple output topics, how would I actually perform this atomic write? So basically, all writes that are part of the transaction need to be committed, or they can be aborted, but the idea is if they're not all committed, then they shouldn't be visible to a downstream consumer. So here's how we're going to do it. Basically, if I'm the producer over here and I want to write to these two topics, topic 1 and topic 2, in step 1, I do this thing where I go and initialize my transaction or my intent to do so to a component called the transaction manager. So we mentioned this in the prior slide. The transaction manager is something that is itself kind of sharded, where it lives on the Kafka broker that holds the transaction log topic for, let's say this producer is using transaction ID X. Then this is going to be the transaction log topic that is partitioned for transaction ID X. So that, it may be X, Y, and Z, but the point is, there may be another transaction topic over here that's holding any transaction entries for A, B, and C. So the point is, the transaction log is going to be partitioned by the transaction ID, and so that tells us deterministically which transaction manager we should live to. This is just going to be a separate process running on the same broker as the leader of the transaction log topic for transaction ID X. So we go and reach out to the transaction manager, which is then going to say, okay, we're now going to initialize a transaction for ID X. Cool. So in step 3, once the producer does that and the transaction gets initialized, the producer can actually write data to the topics. So let's say we go ahead and write this data right here to topic 1 and that data over there to topic 2. Once that's complete, we can now go back to the transaction manager and say, okay, listen, we wrote all of our data, let's go ahead and commit this. The transaction manager, in turn, is going to now add an entry called start commit into its log, indicating that, okay, we've reached the commit point. Even if this guy goes down, a new transaction manager is going to come up from one of the replicas. Keep in mind, this entire log is being replicated as well, just like a normal Kafka topic. We're going to see that there's a start commit, and when the new invocation of the transaction manager comes up, it's going to see that we started a commit. And then, regardless of whether it's this guy or the new one, we're going to run step 6, which is writing all of these commit messages at the end of all of the relevant output topics. So in this case, we've written some data. We also need to write a commit marker to each topic. And then finally, the transaction manager, once it completes step 6, is going to go back to the log and say, hey, we're good to go now. Everything is completely done. We're back in a good state. Great. So I've kind of described a two-phase commit process here, right? Whereby, this guy is writing when we're starting the commit in the log. It's writing when we're ending. The second that you start the commit is kind of our commit point, because it means that all the data has been written to each topic. In theory, if for whatever reason there was an issue, instead of writing these commit messages here, the transaction manager could also be writing abort messages there. But ultimately, this kind of means nothing, right? Like I've explained how there's this data in topics now and there's these commit markers, but ultimately what really matters is how we read it, because the guarantee that we're trying to hold here is that any data like this cannot be read until the appropriate commit marker is written. That's what makes it atomic, because these commits are written to all the topics atomically. Great. So now let's go ahead and talk about reading transactional data. So note that if I'm a Kafka consumer and I'm reading, basically the data from topic 1 and topic 2, I am only going to basically listen to, wait for these commit markers once I am set up in read committed mode. There's also read uncommitted mode, which basically says, just act like normal, read every single message as it comes in. So basically what we do is, let's imagine I'm a consumer and I see this marker where it says like, hey, start a transaction for transaction ID X. Then I've got some data and that's for transaction ID X. Then I got more data and that's for transaction ID X. Let's imagine this end marker hasn't actually come in yet. When I see the start transaction ID X marker, if I'm a consumer, I'm not going to read any more messages from this Kafka topic until this end marker that's corresponding comes in. Now I imagine there's some sort of like in-memory hash map or something that has all of the ongoing transactions, just so that when that comes in, the consumer can then say, okay, this guy has been resolved. Let me now go ahead and read the data, and now we're good to go. Now note that you might think, oh, if I were the consumer, what I would actually do is read all these 3 messages, put them to the side, and then wait for this guy to come along. In reality, that could introduce a lot of memory pressure on the consumer, right? Because now all of a sudden it has to buffer all these messages in memory. And if the consumer doesn't have that many resources, that may be problematic. And since we have to process everything in order in the log anyway, we'd effectively be buffering a bunch of messages while waiting for this guy to come in, and then it never actually does, and then we're in trouble. So instead, it's better to just do broker-side buffering. One of the beautiful things about Kafka is that we don't really care if we start getting behind on it, because it's got plenty of space, right? Everything is disk-based, so we can let ourselves get behind and then catch up sometimes later. Let's talk about the performance of this a little bit, because you may be thinking, oh, Jordan said the words two-phase commit, which probably means that it's really expensive, right? Now, technically, it could be expensive, and it certainly would be if we ran transactions all the time. But in reality, what we prefer to do is run them in batch. Now, if you think about it, and we go back to this write process, regardless of how much data is written to this topic and written to this topic, we're still going to be writing the same amount of commit messages to every single topic here. We're still only writing one commit message to the transaction topic over here. We're still communicating with the transaction manager the same amount of times. So basically the idea is, if we write a lot of data in every single transaction, the overhead of actually performing the transaction relative to the amount of data written to each topic becomes even lower. As an optimization, Kafka does a couple of things. Number one is that basically rather than sending as many messages as there are topic partitions, it'll only send as many messages as there are unique brokers that all the topic partitions are hosted on, and then the broker itself will fan out the messages to all the topic partitions. Cool. So basically the idea is we want to perform batching, because the less frequently that we run transactions, the less it's going to affect our throughput in our Kafka queue. So one stat that the articles all like to repeat, I'm sure this has gotten better by now because this is a pretty old article, is that basically if we're producing 1 kilobyte records and committing them every 100 milliseconds, we only actually have a 3% degradation in throughput. Obviously, that's in contrast to running a commit every single time we publish a couple of records. So this is going to be much better. Of course, there is a downside to this, right? Like, it's nice that we can publish these messages in batch, but what it means is that if we're waiting a while to actually publish this end marker right here, it means that the consumer has to wait longer before reading all the messages that come before the end marker. The last piece of this that I'm going to talk about before we conclude this video is going to be stateful consumers. So basically, you might be thinking to yourself, all right, Jordan, well, you've spoken about read, process, write, which is basically read, have some stateless process or stateless function running on the input message, and then publish that to some sort of output topic over here. But then, what if we wanted to do something where we actually maintain state based on these messages? We don't have any fault tolerance if this consumer goes down. Well, actually, that's not entirely true, because our state itself can be abstracted away like a Kafka topic. When you have state and we cache it in memory, you can think of it like almost like, take a database, for example. A database is like applying all entries of a write-ahead log to a hash map. In the same way, that's what cache state in memory is. So if we represent our cache state basically like a Kafka queue, where we've just got a bunch of write-ahead log entries, and then whatever we're storing in memory is just applying that write-ahead log to our in-memory hash map, then all of a sudden we have state, right? And so now in reality, our Kafka transaction is basically read here, commit outputs over here, instead of saying read, let's say process here, and then we're actually committing to this write-ahead log, so this is kind of like the output here. And then we do the same exact thing on the other side. We're basically committing offsets. Sorry, I wrote output here, I meant to say offsets. Committing offsets, we're doing some amount of processing from this internal write-ahead log to the output, and then we're syncing over here. So now instead of thinking about this as just an input and an output Kafka queue, we can think about it as 3 different Kafka queues, and we have transactional semantics between every single pair of them. And so that way we can maintain state in memory. Okay, to conclude, transactions are extremely important. The reason being that a lot of the systems design interview problems that we talk about do want exact results. Sometimes it's good enough to be like, oh, this is fine to do at least once, or like it's fine if we write to this topic, but we'll write to this other topic after this one because if we reverse the order, that would be bad. The truth is, a lot of the time you can just kind of rely on these transactions, and as long as everyone is using transactions and you're using read committed consumers, then things are going to be okay. So it is ultimately something that I want to kind of circle back and integrate into a lot more of my systems design interview questions, because as you can see, it doesn't actually make a huge hit on performance. And so if it's going to greatly simplify your design to use a technology like this, you should probably do so. And I think there are many opportunities that I get to go back and say, hey, maybe these transactions would actually be better. Kafka is a popular enough technology and it's used in enough of these designs that I think it's fair game to be like, I want to use Kafka transactions. But at the same time, it's not a feature that is necessarily something that everyone knows about, so I think it's good to cover. Anyways, guys, I hope you enjoyed the video. I think this is hopefully a nice sample of what I'm talking about when I say, ultimately I want to talk about in-depth technologies, but also make them pragmatic for using them in a systems design interview and simplifying our designs further. Hope you guys have a great week, and I will see you in the next one.